Hi everyone, I'm Jake, and today I'm going to show you how to do all things calibration related with our VR avatar that we've been building in Unreal Engine 5. By the end of this video, you're going to have height calibration, where you can either choose to scale the skeletal mesh's height to match the player's real-world height, or you can scale the player's in-game height to match the skeletal mesh's in-game height. We're also going to have seated calibration and arm length calibration and joystick crouching so that your seated players can crouch as well. And this is all going to be integrated into the multiplayer VR pawn that I've been building as a part of this tutorial series, so check out my past videos if you need to catch up. I want to thank my Patreon members. I would not be able to spend the time developing, recording, editing, and publishing these tutorials if it were not for them. They get access to all of the project files, they get every video early, and they get higher priority tutorial requests for what I make in the future. So please consider supporting me on Patreon if you want to see me keep making these videos. Thank you. Now, the first thing we want to do in here is create the new inputs that we're going to need. And that's going to be input action. I'm going to call this one IA_calibration. And we can just leave this as a digital bool with no modifiers. And then we need another one for crouching. So we're going to call this IA_crouch. And this one is going to be a axis 1D with a dead zone modifier. And I'm just going to leave that so that it only triggers between 0.2 and 1 in a given direction. Now we want to add these inputs to our input mapping context. So I'm going to do that with IA calibration and IA crouch. These are the inputs that I've assigned to them. For calibration, I want to calibrate by just clicking in my right joystick for now. So that's going to be the right thumbstick button, or the equivalents that I've found for Oculus, Index, Vive, and Mixed Reality. And then for crouching, I want to crouch whenever we move our right joystick down. So that's going to be the y-axis on the right controller for Index, Oculus, Mixed Reality, and Vive, respectively. Feel free to pause the video and copy these inputs if you'd like to use them. Now, the first thing we want to do is go into our animation blueprint, and I'm going to create a blend node off of our output pose. And this is going to blend between the default resting pose and our solved control rig pose. And the reason we're going to want this is because we need to gather data on our skeletal mesh's proportions so that we can calibrate the player's proportions to it, or the skeletal mesh to our player's proportions. So I'm going to create a new Boolean variable, and this is going to be called force resting pose. And I'm going to set this to true by default. And then I'm going to plug this into the alpha for that blend node. So now the skeletal mesh should always start in its resting position until we set this to false. And that's going to be really important for gathering the skeletal mesh's default proportions before it gets all jumbled up with the control rig stuff that we made. Now we're going to go into our custom VR pawn blueprint and start gathering the skeletal mesh data on begin play. So I'm going to add a new pin, and I'm going to add a delay until next tick node. And this is really important because we're going to be getting our skeletal mesh data in component space, but that information isn't available until the first tick because the skeletal mesh hasn't updated on begin play yet. So we're going to delay until next tick, and then we're going to get our mesh. And the first thing we're going to get is a socket transform. And we're going to get the POV socket transform because this is where we want the camera to be. This is where the eyes are. And the way we're going to calibrate height is just by lining up the eye levels of our player and our skeletal mesh by scaling one or the other to the other. So we need to know the eye level for the skeletal mesh. So I'm going to get our POV height and component space. So this is going to give us the mesh's eye height. And I'm just going to take that Z location value, promote it to a variable, and this is going to be our SKM eye height. And then we can set that off of that delay node. Now we're going to need a few more data points to calibrate the arm length. So the first thing I'm going to get for that is our head bones transform. Also in component space, I'm going to recombine this struct pin because we're going to need the rotation as well. I'm going to promote this to a variable, and this is going to be our head bone default transform. So after we get our eye height, we'll set that. And then I'm also going to want the locations for both of our upper arm bones. So I'm going to get upper arm underscore left and upper arm underscore right. I'm going to split these to just get the location. Promote to variable. This is going to be our default left upper arm. And this is going to be our default right upper arm. And we need these because the way that we're going to do arm length calibration is by estimating where the shoulders should be for the mesh. And then we're going to basically look at how far away the player's hands are from the shoulders when we calibrate in an outstretched position. And then, in order to actually scale the skeletal mesh's arms to the player's arm length accordingly, we're going to need the length of the skeletal mesh's arms. So I'm also going to get the lower arm sockets as well. I'm going to move all this up here. Make sure the mesh is our target for all of these. So this is going to be... Oh, sorry, we actually only need to do this with one arm. We don't need to do this part with both of them. So we're going to get lower arm right, right, and our hand right, and these are going to be in parent bone space. So basically, this location, if we distance it from 0, is going to tell us the distance between the upper arm and the lower arm. And then if we do the same thing for the hand, because again, they're both in parent bone space, this is going to tell us the distance between the lower arm to the hand. So now if we add both of those together, this is going to give us the skeletal mesh's arm length. So I'm going to promote that to a variable and save that as skm arm length. And those are all of the data points we need about our skeletal mesh in order to do all of our height and arm length calibration techniques. So now I'm going to grab our VR body animation blueprint, and then I'm going to set force resting pose to false so that now it'll start animating, because we no longer need it to be in that resting pose because we're done collecting that data. And now I'm going to move on to the actual calibration techniques. First, I'm going to create a new enumeration, and this one is going to be enum underscore height calibration methods, because we're going to have two options. Scale SKM to player, or scale player to SKM. And both of these different methods have their own use cases. For example, if you're making a competitive online multiplayer game, you might want all of the players to be the same height in game so that nobody has a competitive advantage. So in that case, you'd want to scale the player to the skeletal mesh's height. But if you're making, say, a social game or an experience like sandbox VR where everybody's in the same physical space interacting with one another and the world around them, you'd want them all to be their actual height. So that's when you would scale the skeletal, or that's when you would, scale the skeletal mesh to the player's height. But now I'm going to go back into our custom VR pawn. I'm going to create new variables for our height calibration method. And that's going to be the enumeration that we just created. And by default, it's scale skeletal mesh to player. And then I'm going to create another variable. This one's going to be a Boolean, and this is going to just be whether or not the player is seated. And then one more variable. This one's going to be an array of transforms, and this is going to be the calibration pose. And that's going to be an array of transforms. Now we can actually get started on the calibration code. So the first thing we need is our input action for our calibration. And then I'm also going to create a custom event called apply calibration. And then I'm going to create one more custom event called replicate calibration. And so basically what we're going to do is whenever the calibration action is triggered, we are going to set our calibration pose. And this calibration pose is going to be the relative transform of our headset and controllers. So I'm going to make that array. It's going to have 3 pins, and it's going to get the relative transform of our camera and each controller. And I'm going to put those into 0, 1, and 2 respectively, following the key that we've been using. And then for multiplayer purposes, we're going to call that replicate calibration event. And to do this, we're going to send our calibration pose to the server. Is going to be that array. And we're also going to send the calibration method and whether or not the player is seated, just in case the player changes those things. So let's do height calibration methods. I'm going to just call this height cal method. We can plug that into there. And then I'm also going to add the seated Boolean. And that's not capitalized. That's going to bother me. All right. And that's a Boolean. Then we'll just drag that into there. And so now on the server, we're going to set all of those variables from this replicate calibration function. And then I'm going to change all of these variables to have the rep notify replication. So basically, whenever this variable gets changed on the server, it's going to replicate it to all of the other clients. And then we're going to get a notify function where we can trigger something from there. So I'm going to add the same thing for all of these rep notify functions. It's going to be a branch. And if it is locally controlled, if this pawn is not locally controlled, we're going to drag off a false, then we are going to apply calibration. So I'm going to copy this and put it into the rep notifies for all 3 of those variables. And so basically what's going on here is when we calibrate, we're going to get our calibration pose and we're going to send that along with our other calibration data to the server through this event, which we need to set to run on server. And then that will then set those variables on the server, which will be replicated with notify, so that on the server and on all of the other clients, we will then apply calibration once those values are updated. And then I'm also going to apply calibration on the local instance when this is triggered. So now we can actually build out our calibration function now that all of that data is replicated and ready to use. So when calibration is triggered, the first thing we want to do is check whether or not it's calibrating seated. So I'm going to create a branch node here if I can type. There we go. And if we are calibrating seated, then we are going to need the camera's eye height, or camera height, from this calibration pose. So that's gonna be 0. We're gonna split that struct pen so we can get that Z location. This is gonna be basically just the player's eye height in the real world. And then I'm going to take our skeletal mesh eye height. We're gonna subtract the player's eye height from that because we're gonna be moving, if the player's seated, then we're going to be moving the play space up so that their eye height aligns with the skeletal mesh's eye height. There won't be any scaling because we don't have accurate player height data if the player is sitting down. So we're going to promote this to a variable, and this is going to be our VR origin seated, I cannot type today, offset. Because it's the offset that we're applying to the VR origin if the player is calibrating seated. So if seated is true, then we're going to set that. If seated is false, then we're going to go to our regular standing height calibration techniques. So I'm going to get our height calibration method. I'm going to add a switch on enum. And so if seated is false, then we're going to go into this switch and execute our code based on whether or not you're scaling the skeletal mesh or scaling the player. So if we're scaling the skeletal mesh, we're also going to need, the skeletal mesh eye height and the player's eye height. And basically, we are just going to divide the player's eye height by the skeletal mesh's eye height, and then scale the mesh based on that amount. So I'm going to grab our mesh, and we're going to set relative scale 3D, and that's going to be that divided value. And that's all we need to do there. And then to scale the player to the skeletal mesh, it's just the opposite. We are going to divide the skeletal mesh's eye height by the player's eye height, and then set that as the scale for the VR origin. There we go. And if you see me looking off to the side a little bit, it's because I have all of this pre-developed on my other monitor so that I can reference it for the video so I'm not all over the place. Just so you know. Now we've got our seated and height calibration mostly done, but we still need to apply the seated calibration and account for the changes to our VR origin scale. So I'm going to go to our scale capsule to HMD function, and this uses the camera's relative location, which is a child of the VR origin, and that VR origin scale might be changed now. So to account for that, here you just need to multiply this by the relative scale of our VR origin. I'm just going to grab the Z, and we can plug that in instead to account for that. But remember, if we're playing seated, we also want to apply that VR origin offset. And that's going to affect the capsule size too, because that's going to be moving our head up and down. So I'm going to get that, and then I'm going to add this before this divide by 2 node here. So for the capsule size, we're accounting for the change in the scale of the VR origin, and that potential vertical offset of the VR origin, which we're also going to have to apply when we set the relative location of the VR origin here. And that is just a simple addition of that offset to the Z location, just like so. Now let's test it. So when I press play, right now, it should scale the avatar to the height of the player. So it should scale it up a little bit because I think I'm a little bit taller than the default height of the player, which it looks like it did. You could see the arms got a little bit longer. It's a little bit hard to tell because it's not a big change. And now if I switch it to scale player to skeletal mesh, now my eye height should be scaled down to the player or the avatar's height instead, which it seems like it successfully was. Yeah, looks pretty good. Now let's try it with seated. So if I check seated, this height calibration method shouldn't matter. And then when I come in here, if I crouch down like I'm sitting in a chair and calibrate, it raises me to the height of the skeletal mesh. So now I'm standing in game. Lovely. Everything's working as expected so far. Let's do the arm length calibration now. We're going to do this by basically figuring out how long the player's arms are. We already know how long the skeletal mesh's arms are, and then we're going to scale the skeletal mesh's arms to match the length of the player's arms. So we're going to come to our apply calibration event, and we're going to make this a sequence. We're going to apply our height calibration first because that might affect the entire scale of our player or the skeletal mesh in the game. So we're going to have to account for that when we scale the arm length of the skeletal mesh. So we want to do the height calibration first. Then we're going to come into our arm length calibration. So I'm going to create a new Boolean here. And this is going to be called arm length scale. Not Boolean, sorry. This is going to be a float, single float. We're going to set this off of this sequence. And this is going to be a little bit of a larger calculation. We're going to need our tracking source to bone offsets and our calibration pose. I'm going to get 0, 1, and 2 of each of these. So we're going to get a copy of 0. We're going to need 2 of each. So we'll get 0s, 1s, and 2s. We're going to get the 0 of our offset, 0 of our calibration pose, 1 of our offset, 1 of our calibration pose, 2 of our offset, and 2 of our calibration pose. So these should be our heads, or our head, and then our controllers. And then I'm just going to compose the offset onto the calibration pose like so. And this is just going to give us the bone transforms where the bones should be in that calibration pose. So for the head bone, we've got to do a little bit of a rotational shift, just like we have been doing. So I'm going to drag off this into a combine rotators node. This rotation should go into B, and A is going to be 90 in the Y and negative 90 in the Z, and that's just to make up for a transform difference in the head that's always there. And then I'm going to make a transform out of that original location, that rotation, and we'll drag the scale in. And then I'm going to want to get our default head bone location that we got earlier, and I'm going to invert that transform. And so what this is doing is this is calculating where our head bone of our skeletal mesh would be relative to the camera. And then by inverting that from its default pose, basically getting where the root of the skeletal mesh would be if it was following the camera from that default pose. And then we are going to compose that onto our head bone transform to get where that root bone would be. Next thing we're going to do is transform two locations. And these are going to be our upper arm default locations. So what we're doing here is we're finding where that root should be, and then we're finding where the upper arms are relative to that. The base of those upper arm bones are pretty much the shoulders. So if we were to visualize this, you would be in game and you'd have two spheres where your shoulders should be that follow wherever your head is looking. And the calibration pose that we're going to use is we're going to have our arms outstretched in front of us. And the reason I'm doing that is because like we're estimating arm length. It's not 100% accurate. And a lot of games will estimate it from your wingspan, but I find it better to estimate the arm length from reaching straight out because that's when the player is going to be seeing their arms the most. And the only reason we're calibrating the arm length is to give the player a more comfortable first-person experience. And the only time they're going to see their arm fully outstretched is if they're reaching for something, which will usually be in front of them. So it's just, you get a more useful arm length metric by calibrating with the arms outstretched in front instead of trying to estimate from the wingspan. If that makes any sense. I'm so sorry if I'm just rambling nonsense. But anyways, we're going to now take the distance from that estimated shoulder location to the locations of our hand bones that we composed. So that's going to be our left hand, and this is going to be our right hand. So this is the distance of each arm, and we're going to average those by adding them together, then dividing them by 2. And now we have an estimation for the length of our player's arms. And again, remember, because we're doing our height calibration first, our VR origin might be scaled. So I'm going to take the relative scale of our VR origin, and I'm going to multiply that by the estimated player arm length to get the scaled player's arm length. And then I'm going to divide that by the arm length of our skeletal mesh, which we got earlier on begin play. So we're going to take that skeletal mesh arm length, and because we might be scaling the mesh with height calibration, I'm also going to get that relative scale, multiply it by our known skeletal mesh arm length, and that's what we're going to divide our player arm length by, and then we'll set our arm length scale to that. There we go. So quick rundown. We're estimating our scaled player's arm length by finding where the shoulders should be relative to where the player's head is, and then taking the length from the shoulder to wherever their hands are, which ideally will be outstretched in front of them. You could also calibrate wingspan, or you could calibrate and T-pose with this method if you want. I just find that having it outstretched in front is most effective at getting a useful measurement. And then we're just dividing that player arm length by our skeletal mesh's arm length to figure out how much we need to scale the skeletal mesh's arms by to make them match the player's arm length. And now we're going to apply this in our control rig. Actually, to apply this in our control rig, we don't actually need this variable in here. I forgot that we have direct access to our animation blueprint. So I'm going to add our SKM arm length scale float variable to our animation blueprint. And then I will just set that directly from here. So we will set SKM arm length scale on our VR body animation blueprint from this calculated value. So now we can throw this into our control rig. In order to apply this, all we need to do is go into our control rig, create a new variable. I'm going to call it arm length scale float. And then I'm going to go into our solve neck and arms function. And between solving the neck and solving the arms, so before we do that basic IK for the arms, we just want to set the scale of our arm bones to match this arm length scale. And we only want to scale the length of the arms. We don't want to scale the girth or the width of the arms because it does end up looking kind of weird in my opinion. That's something you could play around with if you want. But I'm going to set the scale of our upper arm bones. This is going to be our upper arm left. That's the weight. Sorry. Yeah, we're going to plug this into the X scale because that is the length of the arm. We're going to do the same thing for our upper arm right, if it'll let me. Upper arm right. Set the X scale to our arm length. And now if I trigger that before it goes into our basic IK, I should set that default value to 1. There we go. And now you can see it's going to scale the arms before solving them. But you can see there's that little issue where the arm bone goes way past the hand now. That is actually fixed by the twist bone solution. So you just can't see it in this control rig because we're applying the twist bones in a separate control rig. It'll look a lot more natural in game once we actually have this going. But now, if I go into our control rig and I make this variable public by clicking on that little I can now expose that arm length scale pin on our control rig node and plug in that value there. So now our arm length calibration should be working. But first, so that we don't start out with no arms, I'm going to set the default value of our arm length scale variable in here to 1 as well. And now if I press play and get into game, if I outstretch my arms in front of me, you can see they stop about, or they straighten about here, but I still have quite a bit further that I can go. So if I fully outstretch and then click my right joystick into calibrate, now my arms stop stretching when my real life arms do. It looks a lot more natural. They match my arm length. That's perfect. Working exactly as expected. Now we want to do the joystick crouching so that people who calibrate seated can still crouch up and down, or if you just want your players to crouch up and down easier, you can do that. So I'm going to create our IA underscore crouch event. And basically, whenever this is triggered, I want to create a float variable. And I'm going to set this as I'm going to call this our target crouch, because this is going to be different from the actual crouch value. I want to interpolate the actual crouching so it's a lot smoother than your joystick data is. So whenever this is triggered, we want to set our target crouch. And this action value is going to be 0 when your joystick is in the middle. When it's all the way down, it's going to be -1. When it's all the way up, it's going to be +1. I only want the 0 to -1 range. So I'm going to clamp this action value from a minimum of -1 to a maximum of 0 and set that as our target crouch. So 0 is going to be no crouching adjustment at all, and -1 is going to be crouched fully. And whenever this is canceled or completed, I want to set our target crouch to 0, because sometimes when you let go of the joystick, it won't always trigger when it's at 0. So sometimes you'll just be stuck like crouching a tiny bit with this method. So when setting it to 0 when the input action is canceled or completed fixes that. Okay, but now we just need to interpolate and apply that crouching data. So once again, I'm going to go to our scale capsule to HMD function. That's where all of this adjustment is happening. I'm going to create another float variable. This one is going to be our actual crouch value. And this is going to be the interpolated value. So I'm going to set this before we do anything else. I'm going to use a finterp2 node here. The current crouching value is going to be our actual crouch. The target is going to be our target crouch value. Delta time is going to be get world delta seconds. And I'm going to use an interpolation speed of 3. I've found that that works nicely. So now, whenever we move our joystick down, it's going to smoothly interpolate from 0 to -1. And we also want that smooth interpolation because we added that dead zone. We don't want it to just snap from 0 to 0.2. So this will help with that as well. And now to apply that, we can't just offset it by -1 because that's not very much, that's not an effective crouch. We want it to be a little bit more than that. So I'm going to calculate an amount that we want the player to be able to crouch by. So I'm going to take our mesh. I'm going to get its scale. And I'm going to get our skeletal mesh eye height and multiply it by that scale. So we're just taking our scaled skeletal mesh eye height, and I want the player to be able to use their joystick to crouch to, let's say, half of the body's height. So I'm going to divide that by 2. And then, so let's say the skeletal mesh is 160 units tall. This is going to be giving us 80, value of 80, which we can multiply by our actual crouch value. And then we can just add that in with our VR origin seated offset here. And I'm also going to add that to the VR origin offset over here. And now if I press play and move my joystick up and down, you can see we are effectively crouching and our capsule is scaling with us. So if I walk up to here, I can crouch under it with my joystick. It's not letting me through. I can crouch physically, or I can just crouch with my joystick. And it works lovely. And I believe we've set everything up properly to work with multiplayer. So I'm going to test that as well. Let's do this and that. So if I move the second client back, should be able to watch the first client. We're moving fine. Okay, it's working, and we can calibrate properly. But you can see we've got a couple issues. When we crouch, we're getting a bunch of jitteriness in our feet. And we're also getting a weird issue where our hands are moving in front of the capsule when I just move with the joystick here. So let's fix both of those things. First, I'm going to fix the crouching jitteriness. And part of that is just some data roughness. I tried to make the capsule Z height, or like the capsule half height, compressed just to save some network traffic by switching it to a byte. instead of a float, but I think that just creates more trouble than it's worth. So I'm going to change this value on our VR transforms to server to a float. Get rid of that byte rounding. Actually, I can get rid of that clamp too. We don't want that either. So we'll just send that over as a float. We will change this capsule Z relative value to a float as well. And then we will fix all of the errors that creates. We will get rid of the byte conversions. And there we go. Then there's another thing I want to do in here for that. Rather than using the interpolated replicated camera transform, I'm going to use just the raw replicated camera transform for the at least just for the capsule component transform, because it's just there's just too many layers of smoothing otherwise, and it just makes the capsule really like soft and flowy more than it should be. And then for the capsule half height, rather than using that capsule Z relative, I'm going to get the capsule components world location. And I'm going to subtract that from our new camera transform local variable. So I'm going to break this. I'm going to take the Z height of our camera and the Z height of our capsule, and I'm going to subtract the capsule from the camera and use that for our half height. And now, if I press play, if I move this over here, and this here, move this over. Now, the up and down movement is a lot smoother. There's a lot less jitter in the feet on the ground. But you can see there's a lot of side-to-side jitter with the capsule, and the arms still move too much when we move around with the joystick. So I'm going to fix that as well, and that's going to really polish up the multiplayer experience overall and bring it to something a lot more game-ready. So to fix that capsule side-to-side jitteriness, I'm just going to drag from the capsule components world transform into the current location for this interpolation node. We can actually just break these and recombine them now, because we're just using this whole location from here to here. And that should fix the jitteriness of the capsule going from side to side, because now the capsule's actually interpolating its transform as well. And then for the hands moving too much, that's happening because we are essentially moving the capsule and then moving the hands, and it's just like we're like double moving the hands, or we're moving the hands extra by the amount that we're moving the capsule. So I'm gonna do what we did with the camera here. I'm gonna take these, I'm going to put them over here, and we're going to calculate the new transform of the hands before we move the capsule. So I'm going to promote this to a local variable. This is going to be our new left controller transform. And this is going to be our new right controller transform. So I'm going to set both of those before we go and mess with the capsule. And then we can plug those in here. Now if I press play, We can have 2 clients here. And they should have a pretty smooth multiplayer experience where calibration and everything works. So let's say I'm short. Calibrate up, because I calibrated seated. It works on the other one too. And then I can use my joystick to crouch, and the other client is seeing that just fine. Let's make sure. I'm just gonna check one of the non-seated height calibration methods. Let's see if the skeletal mesh scales its height properly. So I gotta move this over. Then I'll move this over. And I'm just gonna make myself a little bit taller than I am for visual purposes. And now if I click calibrate, you can see the skeletal mesh got bigger. So now it's about as tall as I am in the real world. And the arms are the correct length. They straighten about the same point as my arms straighten. And that's perfect. Everything looks lovely. I can still crouch with my joystick and regularly. If you want to make it so that standing players can't use the joystick to crouch, that is an easy fix. I just need to find my event graph. You could just add like a Boolean or a branch on this triggered node so that it will only trigger if seated is true, if you'd like. But I'm going to keep that off because I like for the player to just be able to do that regularly. But yeah, I think that's everything. So now we've got 2 different forms of standing height calibration, seated calibration, arm length calibration, joystick crouching, and all of it is smoothly network replicated. Thank you so much for watching. I'm going to clean all this code up now and package it up, send the project files to my Patreon members. Again, if you want to help me keep making these videos, please consider supporting me on Patreon. It would really help me out a lot. Thank you so much for watching. Bye.